So, I'm Dan. This is a talk called A 10-Year Retrospective Operating Ceph for Particle Physics. Was anyone at the Ceph Day in New York? Okay, you're free to leave if you, no? Okay, because this is a repeat, okay. Just about me, I'm a Canadian guy. I have a Dutch name. Actually, I'm Canadian and Dutch, but mostly an imposter when it comes to being Dutch. I did grad school in grid computing. That's before they thought of the good name of cloud computing. It's something else. At the University of Victoria in Canada. Work-wise, I've been CERN engineering staff at since 2008 until, oops, I have to change that present to say 2023. I was the Ceph manager from 2013 to 2022. I was the IT chief architect for the past year, and then since April this year, I'm working now with Clyso from manning the Vancouver office. Community side, Ceph community side, I've been involved in the Ceph board before it was a board, and the foundation before it was a foundation since around 2015. And after the change in leadership of the Ceph project, I've been in the Ceph Executive Council since a couple of years now. You see, this is a background. This is just a very brief intro in case somehow anyone didn't hear about CERN before. It's the world's largest particle collider in Geneva. It's a 27-kilometer ring, 100 meters underground. I used to live right here. This is what it looks like down below, downstairs. Take an elevator, superconducting magnets at close to 0 Kelvin, accelerate protons in opposite directions at almost the speed of light, so the speed of light minus 11 kilometers per hour. They collide at with the momentum of a freight train, and they capture pictures of that in cameras that look like this. This is the Atlas detector. There's a person there. It may or may not be me. And this is what the pictures look like, okay? This is a picture of something called a Higgs boson. This is the particle responsible for mass. This is the thing that won the Nobel Prize in physics in 2013. And the basic game, the name of the game of the storage department at CERN is writing file systems, okay, with and without Ceph a little bit, tracking pictures like this at around 50 gigabytes per second. Okay, so this talk of mine is about 10 years retrospective, and I'm trying to think of the outline for this talk. And okay, this is a bit of a shameless talk, okay? Because around a month ago was a pretty busy time in my life when we were preparing for Ceph Day New York and this event. So I just asked some new web service, what should be the outline for a 10-year retrospective about operating Ceph at CERN? And this cool web service told me what the outline should be, okay? I should give an introduction, I should give a background about the Ceph at CERN, give some kind of 10-year review, highlight some lessons learned, and then give a conclusion. This is like Ceph GPT, okay? Okay, so here's the introduction. And this is totally real, okay? This is the output of this thing. So I will give you a brief overview, talk about the importance, and the purpose of this retrospective, okay? So this is an introduction, okay? This is, it's at CERN we started using Ceph 2013 with a 300 terabytes proof of concept, and then quickly into production, 3 petabytes. In 2014 and 15, we did R&D on erasure coding, before this was erasure coding in Ceph, and striping data for physics data, striping objects for physics data. In 2016 was the first time that we could test Ceph's promise that you could transparently replace hardware. So we replaced 3 petabytes with 6 petabytes of new hardware. By the following year, we had 8 clusters in production in 2018 and 19. That's when we started really going into testing more CephFS and S3. S3, we were like late to get into that game. We scaled out in the last 3-4 years, getting into Ceph with multiple data centers now, business continuity, disaster recovery use cases. And as of now, there are 17 clusters and around 100 petabytes raw disks on the floor. Not used, but just raw disks. Am I right, guys? This current CERN crew here, it's about right? Yeah, it's about right. You'll notice one thing. When we started a decade ago, we had 3 petabytes, and now there's 100 petabytes. In 10 years, that's Moore's law 5 times. So if you double 3 petabytes 5 times, you get almost that number. So what this means is that it's like a fixed budget. We spend the same on storage every year, and that's how you get to that kind of number, that kind of growth. Okay, next part about this. My coach told me to talk about the importance of Ceph in the lab infrastructure, and this is just all of the stickers that you could imagine. This is the lab infrastructure that runs on top of Ceph. You have the platforms at the bottom, the config management, the OSs, pieces of databases are on there, all of the monitoring pipeline and analysis platforms, a little bit of the physics storage. Mostly the physics storage is this thing called EOS, okay, 500 petabytes of data stored. And then, you know, lots of other things on top. Also like web platforms, blogs, blah, blah, blah. The purpose of this talk, because, you know, we shouldn't forget the history. Decades they match what's on your hands. And it's like a memoir because, you know, changing my life. Okay, the second part is about the background. So my coach advised me why I should talk about why CERN chose Ceph as its storage solution, the challenges faced in implementing Ceph, and the overview of Ceph architecture at CERN. Cool. All right, so why Ceph? So in 2013, 2012, just like we heard from the panel here, we had OpenStack, and we were like thinking, what can we use for the storage? And there was an obvious answer. We had tried Gluster and NetApp and Ceph basically won. We also saw that, you know, the reason it won was because we wanted an organic solution, something that would grow with our usage and evolve with our needs. And we didn't ever want to like get a new appliance, a new vendor, and then have to copy all the data, like with VMs down and stuff. This is impossible. I don't know if that problem's solved in the meantime. I'd like to hear afterwards if there's like a solution to that, but maybe there isn't. And also it gives the best bang for the buck. If you've got a bunch of if you've got Linux experts already, then you can take this basic idea, you know, buy generic data center commodity hardware, add software, and you get enterprise storage features. It was like that then, and it's still like that now. Some challenges implementing Ceph. Okay, this is like, yeah. This talk is my personal views on things, okay? This is not official party line of any of my previous or current employer. So the first challenge was CERN buys one particular type of hardware, at least in the early days, in bulk based on the needs for scientific computing. So there was a kind of golden rule in high energy physics, 2 gigabytes of RAM per core at that time, large hard drives as you can get, and always like 24 or 48 HDDs per like JBOD chassis, and it's always the same stuff. It's the same stuff that was there a decade ago as it is today. Maybe the SAS interfaces are now 12 gigabits per second instead of 6, but it's the same stuff, same basic form factor. Similarly, it was like, why do you need 3 replicas, and why do you need a little bit of SSDs here and there? These are the questions asked back then. By now, it's pretty good. Also, like in the early days, there was a strong not invented here syndrome. There's a very talented storage group at CERN, and to use something open source, it was a bit of a challenge. There were ideas like, we only want Crush. We're not interested in Ceph, but the Crush algorithm looks cool. And there were also comments like, you'll never solve latency. The fact that you've got to like now go through, you know, the storage not just being local was a big problem. Yeah, were challenges. The architecture. Okay, so the basic host architecture hasn't changed. We use server quads. So these are these like 3U boxes that have 4 servers in them. And nowadays they've got a bunch of SSD slots in the front, so you can put like something like 24 SSDs. CPU-wise, we use dual socket Xeons or AMDs. The reason for this is because the same nodes are used for batch processing as we use for storage. We just buy the same stuff everywhere and then attach some JBODs when we want to do storage. It's normally 2 gigabytes per hyper-threaded core, so those servers have 256 gigs of RAM now. We started with 1 gig E, and then 10 gig E, then 25 gig E, just like everyone else. We always use a shared public and cluster network. We've never needed a dedicated back-end networks for Ceph. We've always used dumb HBAs, never RAID cards. Where's Luca? He's here. There he is. Never RAID cards. And then 1 or 2 24-disk JBODs. Since the beginning, we recognized that you need to accelerate something. So with file store, we had a journal. This was like a 10 gigabyte journal at the beginning to cache like up to maybe a minute's worth of writes, to buffer about a minute's worth of writes. Now we use it for the BlueStore, BlockDB, and WAL. Originally, we were conservative. We wanted, so always data center quality SSDs and NVMe. Originally, there were 5 drive write per day with 5 OSDs on each, like 5 OSD journals, let's say, on each SSD. Now you can get by with like around those 1.3 drive write per day NVMEs or flash devices, and we're totally comfortable putting 12 OSD BlockDBs on each of those NVMEs. This is some photos. So on the left, we have from 2013. This is the original Ceph at CERN. And then 2017, this is a similar row. That's not the exact same row, but you see the architecture is basically the same. And I don't even have a newer photo. It's the same stuff. It just got boring taking photos of the same stuff all the time. Ceph architecture network-wise, originally we tried to, infinite flexibility of Ceph. We put servers kind of everywhere, clusters spanning switches, routers. We didn't really pay attention to the network level. Nowadays, we try to contain clusters behind one switch because most of the outages that we ever had with Ceph were related to network issues. Mostly they were router line cards failing or like half failing, corrupting packets, doing weird things. Ceph always survived those, but this would cause flapping OSDs. So generally, I found, at least in that environment, it's better that a cluster is like fully down. So if there's a network issue, just like make the whole cluster inaccessible rather than flapping up and down and then having to clean it up when you get to work in the morning. Originally, we had one cluster for everything across all of those networks, but now we have several clusters, several zones. This is something, I'll come back to this on another slide, but Ceph is pretty good at staying online, but as we get more mature application developers, like your app should learn about downtime budget. They should use resources and they should know that they're not going to be up 100% SLA. Okay, next section from my coach here. 10-year review of Ceph at CERN. So performance and scalability, upgrades and improvements, challenges faced, and some success stories. So performance. I summarize Ceph performance as saying it is what it is. Most of the time, people new to the community, like they buy some nice NVMEs getting like 500,000 IOPS, and they expect Ceph to give you 500,000 IOPS, and they just ignore all of the complexities that Ceph is solving for you transparently. We host so many different use cases in a Ceph cluster. So I guess I don't think you don't need, Ceph doesn't, it's not a big problem that Ceph doesn't give you millions of IOPS. If you ask users what performance they need, most of the time they don't even know. They don't understand their workload. They don't understand their requirements. They want like a local NVMe performance, but in practice, really since the beginning, we were throttling the block devices to 100 IOPS, and most applications were happy with this. Now we give up to like 500 IOPS, and they're mostly happy. We're not running like super IO-intensive databases on top of this exact solution, but for the bulk infrastructure, all of those stickers that I showed on an earlier slide, it works pretty well. That said, there's some there's like an elusive dream that every operator or let's say decision maker has. They just want to add like a flash tier. We've heard about cache tiering today a few times. With file store, it was actually pretty easy to speed up writes but not reads. There's different usage of bcache around. I know it's used in production sometimes now. I think it doesn't work out of the box. Okay, there's some, because I worry about how data scrub works in that case. If you go through some device that's proxying the real bits. Okay, maybe this is technically fine, but I would just like to confirm that. There was a question earlier today that I wanted to, during I think my colleague Joachim's talk. The configurations in Bluestar are related to deferred writes. Okay, so deferred writes is the thing that Bluestar does for objects smaller than a certain threshold. It just puts them on the SSD, just like the good old days with file store. But I think that this could be used more. There was a bug related to this in Pacific, which is fixed so far, but I think that we could do more to get like SSD performance with a small cache, with a small block DB. You know, we see it in other file systems like ZFS. You can add an SSD to a big cheap box full of HDDs. You can add an SSD or an NVMe there for the L2 cache, that's a read cache, or the Z log, that's where it writes, and you can like add them on the fly. And it just seems that Ceph should have a feature like this. I was happy to hear Sam mention that this kind of thing is planned for C-Store for the Crimson backend. So that's cool that we're going in that direction. There is one thing, though, related to performance that I wanted to point out, because this was the coolest thing that happened in the last, let's say, 18 months. This plot is showing the latency to our oldest, biggest bulk cluster at CERN. It starts, you know, unfortunately, I only have the plot going back 5 years. This cluster is 10 years old. But there's basically a probe that runs every minute and just does Rados bench, 4 kilobyte writes with one thread, and then it just records the average latency to this graphite monitoring system. And you see, it was always under 10 milliseconds, and then as the amount of data, number of like volumes mounted increased, it's now up to around like 8,000 volumes there on that cluster. It was increasing and going up, you know, in some cases going above 100 milliseconds for weeks at a time. Okay, by the way, nobody noticed or complained this whole time, because when you have a block storage cluster, most things are cached locally on the local Linux on the VM, right, or whatever the OS is running. But at around this time, late 2021, early 2022, we noticed like a real problem adding a new generation of hardware. So it doesn't look like a problem, but that's because we fixed it also. This doesn't show the main problem. The problem was actually latency it became unusable as we put in a new generation. It was some AMD EPIC boxes, and we thought that it was a CPU issue. After a few weeks of like testing different BIOS configurations, different PCI configurations, eventually we thought, like why don't we just turn off the write-back cache on these drives in these machines, and that provided that fix. Okay, that's how the cluster went from giving 75 milliseconds of latency down to around 3 to 5 milliseconds of latency with the same workload, just switching off the write-back cache. And this was so dramatic that it was like too good to be true. So it took us something like 3 to 4 months of talking to different members of the community. Did they see the same thing? We eventually got in firmware engineers from the drive manufacturers to try to explain this, and they confirmed that yes, if you have a write-back cache mode enabled on the device, then Linux needs to call fsync on that device, and when that calls fsync, it's going to flush the entire write-back cache of the device down to the spinning media. This is very expensive. So if you have the write-back cache off, now every Linux sees this drive in write-through mode, and it doesn't issue fsync anymore because it just trusts that the device is going to persist this. But you would think, that means the drive is going to be much slower, but actually it has some like acceleration firmware and a special like flash unit that it enables in that case, and it just caches writes, it buffers writes internally in a much quicker way. So it turns your spinning disk into like an SSD kind of thing. You can get, basically, if you have data center quality HDDs, around 14 terabytes and higher, they all have this. We've had it on Toshiba, Western Digital, all the different manufacturers have the same feature, and you get something like, in the way that Ceph uses block devices, you go from something like 30 or 50 IOPS with write-back cache on to around 400 to 500 IOPS if you turn the write-back cache off. So there's a documentation about this on the Ceph, docs.ceph.io. All you have to do is just enable write-through mode, and it's done. Now, scalability. We had lots of fun with these so-called Big Bang scale tests that we did in 2015. We did 2 rounds of this, 2015, 2018. How this worked is we got shipments of new server hardware, and just like Posse's doing now with latest releases, we were doing back in the let's say F and then L releases. There were many problems initially in these tests. This is where we learned that, with 10,000 OSDs, the maps are too large and Mons couldn't keep up serving the maps. The OSD peers couldn't actually discover the maps and peering was flappy. Clusters were completely inoperable above 2,000 OSDs, but the team used this, logged in, used this playground to make things much smoother. Also, this was along the time that the manager daemon, everyone just uses the manager daemon now, but like, what is that even? All the work that the manager does used to be done by the Mon. So the Mon used to be much busier than it is now. So the manager offloads all the non-critical work from the Mon, so the Mon can just do its one single job, send out the cluster maps. And also, that manager is cool because with this thing on the side, you can have Python developers, which there's lots of skilled Python developers out there to add features to Ceph. But anyway, still more than a couple thousand OSDs is probably not the best practice for other reasons. When we went from file store to blue store, this was a huge improvement for a Ceph operator. File store was convenient. You could ls the directories and see what was going on, and you could try to break Ceph by VIing the file or Emacsing the objects and then you could gain trust in the system. Operationally, there were lots of problems like collection splitting. If anybody ever had this kind of, if anybody knows what that means, this was as you grew in OSD, file store became pretty nasty. But the main thing that BlueStore brought was checksums. We didn't have end-to-end checksums in Ceph until we had BlueStore. So we couldn't trust that we were actually serving correct data. If there was a bit flip on the primary, we would serve out bad data in the past. Now with BlueStore, we're good. It is still, of course, scary. I mean, if anyone just came from Adam's talk, you saw there's still some interesting bugs that happen. But it's really cool that there's those low-level gurus that can fix this stuff. So cluster operations is pretty civilized nowadays. As Ceph improved over the time. CephFS was almost awesome for a long while. It was the last out of all of we used to talk about different components of being awesome, almost awesome, whatever. This was the way that we made it sound cool. CephFS was the last to become awesome, and it's still probably trailing behind in its awesomeness, I would say. But it's pretty cool. Challenges. We learned very early on to apply changes to your clusters gently, okay? In a large cluster, you're always rebalancing data. If you get new hardware, this is a many-month intervention. One of the best practices we learned is you need to aim for health okay, at least with no backfilling, at least weekly, because that's when the Mons can trim maps. If Mons are accumulating maps, this becomes a disaster. So don't flip any switch that's going to take a week or a month to resolve. We made lots of tooling, like gently reweighting things, gently splitting PGs. Nowadays, Ceph manages itself. So this is all irrelevant stuff now, but it's just interesting things along the way. But it is still too easy, in my opinion, to change a 1 to a 0 in a crush map, or even with a command line, change one little thing. You think it's harmless, but you trigger some condition that takes weeks to resolve. I think Ceph needs some kind of wrapper like Nomad and Terraform have, where you prepare a change, it tells you what it's going to do, and then you can apply it if it looks sane. I think we need that. Other challenges we had along the way was non-uniform data placement. This was for a long time like the problem when you got to scale, because if you had a multi-petabyte cluster, you had 10% variance. It meant you lost like a petabyte of storage. I mean, that's expensive. So that's why the upmap balancer came up. Now you just type like Ceph balancer on and magic happens and things are, for most cases, things are good. But there is like, my favorite like nerd thing to say is that Crush is fundamentally broken. There's old, if you can search through the email archives, the mailing list, search up this thing called the multi-pick anomaly. Crush has some kind of flaw, but upmap works around it. Ceph is fine. This is not a flaw in Ceph anymore because our balancing makes it work. They're not perfect in all scenarios. There's a really cool script by the JJ. Is that a person in this room right now? No. There's a really cool script by the JJ to balance things if the upmap balancer is not good enough. There's also, like, if you are really curious about Ceph, when you dig into how upmap works and how the balancers work, you can like actually realize that this is like a tool that you can use to put data wherever you want. And you can, without breaking, let's say, fault the failure domain rules of the cluster, but you can fill up disks however you want to. So you can script things, and there are different examples of scripts. We wrote one called upmap remapped, which is a tool used to like pause things where they are right now. If you've got balancing ongoing and it's going to take like weeks to resolve, you can run a script. There's upmap remap. There's also PG remapper, a tool from DigitalOcean that let you just pause things, and you can go for your Easter long weekend and then come back the next week and continue the migrations. Scaling CephFS remains a challenge. MDS is single-threaded, so you need many of them. Multi-MDS is stable, like when you're not changing it, but like adding and removing number of MDSs is like a scary thing for a CephFS operator. And the balancing heuristics are not perfect. So I think most people like don't just like put multi-MDS and let it go. You need to think about how you want to, like, maybe if you've got user home directories, you need to pin them, or use this ephemeral pinning feature to like map them across your MDSs so it stays pretty static. We don't have like an idiot-proof, a Dan-proof CephFS recovery tool. There's great documentation about it, but it's very like low level and scary. Also, snapshots that they're a point of no return. Once you enable them, it enables some data structures inside that are a little bit scary. S3, if you're scaling one region, it's not very hard. I heard today from the Platina folks that if you need a large scale open source S3, then Ceph is the obvious choice. Okay, that's really good to hear. And that I agree with. The CERN stack for this is we use a front-end load balancer called Trafic that routes to specific Rados gateways depending on the bucket names, because we have sort of patterns in the bucket names for different large user communities. And this prevents the user communities from like DOSing each other by DOSing the Rados gateways. We've had a few bucket index issues, but no big problems. Multi-region S3 is difficult. Okay, we heard from Bloomberg there. They're the pathfinders on that one, I would say. Now, another challenge is, this is like the most memorable challenge that we had. Okay, so Ceph makes it very simple to put all of your use cases, everything into one cluster. But we heard somehow like maybe your grandmother told you don't put all your eggs in one basket. We learned that lesson the hard way. So there's a YouTube video that we did during, the video was while we were all locked down, but this was an incident in February 2020. And what happened was there was a bug in LZ4 library, which is used by Ceph to compress objects. I think what happened was, around December 2019, I typed Ceph like OSC compression on, and then that like everything was fine compressing the objects, but then in February 2020, all the OSCs of the cluster crashed. And they crashed because all the OSC maps got corrupted. And that was a downtime of 8 hours. Eventually, we fully recovered it by extracting out an old map and injecting it in. And now that kind of bug will never happen again, so that's good. But anyway, this taught us don't put everything in one cluster. You need many storage availability zones, we call them. Yeah. Successes, so why did Ceph succeed in that environment? Because it integrates with the platforms. OpenStack and then Kubernetes, the OpenShift, all the containers, native stuff, and not to mention, POSIX through CephFS and S3. It also succeeded because it protects the data. It's reliable. There's so much crazy stuff that happens to a data center over the years, but I don't think we've lost any data. I don't think we ever did. Did we lose any data? I don't think so. Yeah, Abby's saying no. Yeah, I don't think so. So thousands of apps are trusting it as a core building block. Trusting it too much in the sense of availability, let's say, you still have outages so they should be redundant across AZs, but otherwise it's reliable. It succeeds because it continues to grow. Those same original clusters are still growing. We replace them every 5 years with new hardware, and they get bigger and bigger and bigger, migrating volumes sometimes between or files between, but largely it's just growing. And of course, because of the friendly and knowledgeable user community that we love here in Ceph. Strong community is good for everyone. This year we have already 6 confirmed in-person events. We've done 3 of them. There was one I missed this morning. There was also one in Southern California last month. And there's 3 more planned for this year, and then we're already talking about a few more this autumn. Okay, we're going to get back in the good old days. We had something like more than a dozen Ceph days per year. It looks like we're getting back to that. That's cool. Okay, that was a long section. Let's see. How much time do I have? Yeah. Okay, so now this Ceph GPT is telling me I should talk about my key takeaways from 10 years of operating Ceph at CERN. Okay. I don't know. Let's see. Let's ask, what were my key takeaways from running Ceph at CERN the last 10 years? Oof. Running, I know this is an old joke right now, but it is scary, this thing, right? And this is only ChatGPT version 3.5. There's already version 4 out, and it's even better answer. But I think I could have written this myself. Maybe I did write this somewhere, and it copied it. Because it says, here's what I've learned in the last 10 years. Proper planning and design are critical, POCs, right? Monitoring and maintenance is essential, regularly checking for hardware failures. Resilience is key. Set up appropriate replication or ratio coding schemes, configure failover mechanisms, proper data placement. Okay, testing is crucial. Okay, the POC thing. Collaboration is important. Oh, it's complex, so you should actually collaborate with other organizations who have experience. Participate in open source communities. Attend the conferences. Share best practices. Overall, you probably got a deep understanding of the technology, and you can apply them to future deployments. Wow, okay, that's amazing. I don't know what we're doing. Okay, so this is the end of the talk. I ran out of time. So I would just like to thank all my CERN colleagues that helped build the IT and storage infrastructure, made that, 15 years working at CERN was amazing, really. Thanks to the Ceph community members, and to the developers. Thanks a lot. I think we have time for questions, yeah. There is a mic somewhere.
Two questions regarding the data. First, just for me to understand, the data you're collecting are after a trigger, not everything collected, just what is.
Yeah. Okay. So this I'll take as okay. So just to make it very clear, Ceph does not store this 100 petabytes. This is infrastructure data. Okay. Ceph is not storing the particle physics data. But I'll happily answer your question. Okay. Yes, it's triggered. Those collisions are more like 1 megahertz. Each of those photos that I showed at the beginning is around a megabyte. And at 1 megahertz per detector, is it 1 megahertz? 40 megahertz. Yeah, because it's 25 nanoseconds is that it? Yeah, 40 megahertz. So that's like 40 gigabytes per second? No, 40 terabytes? I don't know, someone do that math. 9 hours jet lagged. Yes, there are multi-levels of triggers that look at those collisions and throw out vast majority of it is noise. In the end, the trigger rate is like 1 kilohertz. Is it still 1 kilohertz? Yeah, it's around 1 kilohertz per detector, yes.
And that's not the data that's stored in Ceph, or is it? Where is it stored?
The particle physics storage system at CERN is called EOS. It's this one. Yeah. And EOS fronts a large tape archive called the CERN tape archive, which is a 1 exabyte tape system.
Oh.
And one copy of the data is stored at CERN, and another copy of the data is distributed out to the global worldwide LHC computing grid, which is 11 or 12 tier 1 centers. CERN is the center. There's 11 or 12 tier 1 centers, and there's, all told, more than 200 universities and labs involved in storing and processing this data. Yeah. That's not a Ceph thing. That's just, curiosity. We can talk after also, yeah.
So my second question is irrelevant.
Okay.
Just as a quick comment, one of those 11 tier 1 sites is actually running Ceph for its storing that data, and I will be talking about it tomorrow.
And there's another here. Yeah. Okay. Yeah. Yeah. Oh, and we've done, I mean, at CERN, it's an ongoing development to bring these different storage technologies together. Yeah. We did, 1 year ago, we did a test with some new 100 gigabit network machines. So like 16 of them, and then like pumping the data as fast as possible, where we layer this like EOS storage on top of CephFS just to see how it can go. And we were like writing at 30 gigabytes per second and reading back actually slower than that, but yeah, just to see if we could do it. And yes, it works. As an architecture, it can work, but we have to it's complicated. There's lots of integration to be done to make this, yeah. Any other questions? No further questions? Thank you.